Ladies and gentlemen, welcome back to lesson 16 in group theory. In this lesson, we're going to be talking about a result which I find very entertaining. This result says a finite subgroup of a multiplicative group of a field is always going to be cyclic. To prove this result, we need to prove first two preliminary results. The first of which says, in a finite abelian group, the order of every element divides the largest order of an element in the group. The second result says, a degree n polynomial has at most n distinct roots. This is something that you might have seen before, but now we get to prove it. The main result is what comes immediately after by using also Lagrange's theorem. So this is also yet another application of Lagrange's theorem, showing the importance of that theorem. Lastly, we will see a very interesting consequence that comes immediately after this result. And this consequence pertains to the nth roots of unity, which we've already seen before to be cyclic. But it's nice to have another layer of confirmation to our intuition. Let's get started. As promised, I will be proving the first result, which says that if A is a finite abelian group, let M be the largest order of an element in A, then every element in the group A, its order will divide M. Let's get to the proof. Let's lay our groundwork for the proof. Let G be an element in A such that the order of G is M, the maximum order an element can have. Since this is the maximum order, we're expecting to prove this using contradiction by finding that there is another element with an order that is bigger than M. And that is the contradiction because it is impossible for any other element to have an order that is bigger than M because M is said to be the maximum order. So let A be another element in A. The proof will be done by contradiction. Suppose now that the order of A does not divide M. We want to arrive at the contradiction using that supposition, which will force us to say that in the end, the order of A does divide M. So having supposed that, there exists a prime P, there exist integers S and R, which are non-negative, such that M is equal to P to the R times M1. The order of A is equal to P to the S times M2, and P does not divide M1 and neither M2, and S is bigger than R strictly. So basically saying that if the order of A does not divide M, then logically speaking, because each integer can be decomposed into a prime factorization, we will find that there is a prime that is in A that is not in M. And that's why we have that S is strictly bigger than R, because the prime that is found here will not be found over here. And we will suppose that P does not divide M1 or M2, thus ensuring that when we write it like this, P to the R times M1, we have taken all of the powers of P from M1 and we put them over here. So for example, if P was equal to 2, then this will be a power of 2, and this will be an odd number that does not contain any 2 in its factorization. Now let two elements in the group X and Y be in A such that X is equal to G to the PR and Y is equal to A to the M2. Now you might ask me, why did I define them to be in such a way? You're going to now see It's because we have that if we take x to the m1 power, we get that this is equal to g to the pr to the m1 power, which is equal to g to the pr times m1, and that is equal to g to the m. But we've said that the order of g is equal to m, being the smallest positive integer, such that if we take g to that power, we get the identity. So this is equal to the identity. And since this is the smallest integer, then this has to be the smallest integer as well. So x to the m1 is equal to the identity being the smallest. So that means, by definition, that the order of x is equal to m1. If you've forgotten definition of order, go back to lesson 3 and check it out. And similarly for y, if we take y to the power p to the s, we get that this is equal to a m2 p to the s. Similarly, we treat y by taking it to the ps power, and this is equal to, by definition of y, a to the m2 to the power p to the s. This is equal to a to the m2 ps, but that is equal to the order of a. So this is equal to a to the order of a, and a to the order of a, of course, is equal to the identity. So we conclude, similarly as in x, that the order of y is equal to p to the s. Now we would like to know what happens if we take xy to the power m1 ps. So since a is abelian, if we take xy to the power m1 times ps, so for x we had the order is m1, for y we had the order is ps, so we will just take the product m1 ps in the power, and because a is abelian, we can distribute this power onto x and y, so this is equal to x to the m1 ps y m1 ps. Remember, this is only true if a is abelian, because then we would be able to commute the elements, and then we could put all the powers of x on the left side, all the powers of y on the right side. And this is equal to x to the m1 ps times y to the ps to the power m1, and this is just the identity to the ps times the identity to the m1, because that is the orders of these two respectively, which is equal to the identity, giving us that the order of xy has to divide m1 p to the s. Now I will claim a statement that says that this not only divides m1 ps, but it is equal to m1 ps. And I will prove this later on. But for now, I will suppose it is true, and I will move on based on that supposition. So using this fact, and using the fact that m is equal to m1 p to the r, and using the fact that s is bigger than r, I can say that the order of xy is equal to m1 p to the s, and because s is bigger than r, then m1 p to the s is bigger than m1 p to the r, and m1 p to the r is equal to m. So we have just found an element in A such that the order of that element is bigger than m, but m is the maximum order as we have supposed. So this is a contradiction. This contradicts the maximality of M. Therefore, we have that the order of A, because this contradiction has been based on the fact that the order of A does not divide M, so we have to have now that the order of A does divide M, and the proof is complete over here, proving this proposition. But now we need to go back and prove the claim that the order of xy not only does it divide m1 to the ps, but equals m1 p to the s. The proof of this claim will also be done by contradiction. What we would like to prove is that the order of xy is equal to m1 times p to the s. So we will suppose the opposite. We already know that the order of xy divides m1 times p to the s. If we combine these two facts, we will find that there exists a prime q such that q divides the bigger number and the smaller number divides the bigger number divided by q. So if this sounds weird, just take an example. So let this number be 15 and this number be 30. We have that obviously 15 is not equal to 30, but that 15 divides 30. So there exists a prime. In this case, the prime is 2. 2 divides 15, and 15 divides 30 divided by 2. So what this says intuitively is that because 2 is found in the factorization of 30, but not in the factorization of 15, then it is quite alright to divide by 2 and still have that 15 divides that quotient. So now let us look at the GCD of m1 and p to the s. We know that p is not found in the prime factorization of m1, so we can say that since the GCD of m1 and p to the s is equal to 1, they are coprime, either q, the prime q, divides m1, or q divides p to the s. And that is because q divides the product. But because m1 and p to the s are coprime, then q is either found in the factorization of m1 or it is found in the factorization of p to the s. And it cannot be found in the factorization of both at the same time, because then that would contradict the fact that the GCD of m1 and p to the s is 1. So if q divides m1, that means necessarily q is not equal to p, because m1 does not contain p in its prime factorization. If q divides p to the s, then because q is a prime and the only primes in the factorization of p to the s is p, then necessarily q is equal to p. So either q is not equal to p or q is equal to p. So if q divides m1, we hope to arrive at a contradiction. How do we arrive there? We have a very nice thing here. Since the order of xy divides m1 p to the s over q, then if we take xy to this power, we should get back the identity by the definition of the order. So the identity is equal to xy to the power m1 p to the s over q. And now we can use the Abelian property of the group A to again separate the x's and the y's. So this is equal to x to the m1p to the s over q times y to the m1p to the s over q. And remember, this is because A is abelian. It would not work otherwise. So this is equal to x to the m1 p to the s over q times y to the p to the s to the m1 over q. The reason I isolated the p to the s is because we know that the order of y is equal to p to the s. So because the order of y is p to the s, this is equal to the identity. And this here is an integer because q is supposed to divide m1. So this is an integer. And if we take the identity to an integer power, we get the identity. So this is all equal to x to the m1 p to the s over q. Great. We now have that x to some power is equal to the identity. So then by the definition of the order of an element, the order of x must divide m1 p to the s over q. But we already supposed the order of x to be equal to m1. So now we have this relation here. We can divide both sides to have 1 divides p to the s over q. So I divided both sides by m1, and now I multiply both sides by q to have q divides p to the s. But if q divides p to the s, necessarily this means that q is equal to p because q is a prime, and then this is a contradiction because we've already said that q divides m1, which means that q is not equal to p. So it cannot be not equal and equal at the same time. So this is a contradiction, and q does not divide m1, leaving us with the only other option to work with, which is q dividing p to the s, or q is equal to p, basically. So if q is equal to p, then we can use this property again to write 1 is equal to xy to the m1 p to the s over q. But remember now, because q is equal to p, we can just replace q by p. And using exponent laws now, we can say that p to the s divided by p is equal to p to the s minus 1. This is xy to the m1 p to the s minus 1, which is equal to, again, because a is abelian, x to the m1 p to the s minus 1, y to the m1 p to the s minus 1. And this is equal to x to the m1 to the power p to the s minus 1 times y to the m1 p to the s minus 1. And the reason I isolated that again is because x to the m1 is equal to the identity, because m1 is the order of x. So this all is equal to y to the m1 p to the s minus 1. Therefore, the order of y is going to divide this number here because y to that power gives the identity element. So the order of y divides m1 p to the s minus 1. But remember, the order of y is defined to be p to the s. So we have this relation now. If we divide both sides by p to the s, we get 1 divides m1 p to the minus 1. And now if we multiply both sides by p, we get that p divides m1. And this is a contradiction because we've just said that q does not divide m1. Therefore, this is a contradiction, leading us to say the opposite of what we supposed in the beginning, which is the order of xy is not equal to m1p to the s, now we are forced to say that yes, indeed, the order of xy is equal to m1p to the s, thus completing the proof of this claim, which leads to the completion of the proof of the entire proposition. Let us move into the second and last preliminary result before going to the main result. Proposition 2 states that if P is a polynomial in T, it's a degree n polynomial with the coefficients ai in a field F, and an is the leading coefficient that is non-zero, then P has at most n roots. In other words, there exist at most n distinct elements alpha 1 to alpha m, where m is at most n, such that P of alpha I is equal to 0 for all I between 1 and m. Let's get to the proof of this proposition. Since we'd like to prove this proposition for any degree n polynomial, we would like to have this proof by induction on the degree of the polynomial. So the proof will be done by induction on the degree of the polynomial, which is n. So by induction, we have two steps. The first one, the easy one, which is the base case, where n is equal to 0. If n is equal to 0, then the polynomial is equal to a non-zero constant, where a is in the field. So there are 0 roots, and of course 0, the number of roots, is less than or equal to 0, which is the degree of this polynomial. So this is already proven. Now, the inductive hypothesis. We suppose that the result is true for n minus 1, and we will prove it for n. So let n be strictly bigger than 0. Because if it is 0, then we just get a constant polynomial which has no roots. Let alpha be an element in the field F. We can divide the polynomial pt by t minus alpha. We can divide pt by t minus alpha using long division to get us a quotient and a remainder. So dividing by t minus alpha gives us a quotient qt and a remainder which we call r to rt. We have that alpha is a root of the polynomial pt if and only if p alpha is equal to 0. So if we replace alpha in the equation, we get that this is equal to 0, so the product here is equal to 0, and we get 0 on the left side, so we get in the end that RT has to be equal to 0. R of t has to be equal to 0. So now we can get the RT out of the way. We get only pt is equal to t minus alpha times qt. Moreover, if we have another root that is different from alpha, then since alpha prime is not equal to alpha, we get that alpha prime minus alpha is not equal to 0. So if we just replace in the equation, knowing that RT now is equal to 0, we get that P of alpha prime, and that is equal to 0 because we've said that it's another root of PT. So 0 is equal to alpha prime minus alpha times Q of alpha prime. So because alpha prime minus alpha is not equal to 0, and the product of these two numbers is equal to 0, then this forces Q of alpha prime to be equal to 0. So this means that alpha prime is a root of Qt. Now, based on this division here, we know that the degree of Qt plus the degree of t minus alpha equals the degree of pt. But the degree of t minus alpha as a polynomial, it's a polynomial of degree 1. So if the degree of pt is equal to n, and this is a degree 1, then qt has to be an n minus 1 degree polynomial. So since the degree of qt is equal to n minus 1, which is less than n, we can use the inductive hypothesis to assume that the result that we're trying to prove, the result is true for qt. qt has at most n minus 1 roots. Let's say these roots are alpha 1, alpha 2, all the way to alpha n minus 1. So this means that pt has at most n roots. What are these n roots? Well, we know that alpha 1 to alpha n minus 1, because they're roots of q, they have to be also roots of p, because p is q times that. pt is equal to t minus alpha times qt, right? Remember, the rt is equal to 0. So if qt is equal to 0, 0 times anything is 0, then pt is equal to 0. So any root of qt is a root of pt. So that means alpha 1 all the way to alpha n minus 1 are roots of pt, and alpha, which is the root of t minus alpha. So basically, this has n minus 1 roots, this has 1 roots. Add the number of roots together, we have at most n roots for pt, completing the proof of this proposition. Now at last we arrive at proposition 3, the main result of this lesson. Let F be a field and F star be its multiplicative group. In other words, we take all the non-zero elements in F, we take the multiplication operation of the field, and we call that the group F star. Then every finite subgroup H of F star is cyclic. To prove this, let M be the largest order of an element in H. We can take the largest order because we know that H is a finite subgroup. So there is no element with order infinity. We can take M, and now by Lagrange, we have that M must divide the order of the entire group. So, because it divides it, it has to be at most the order of the group. So we just proved that M is at most this order. We want to now prove that M is at least this order, thereby proving that M is equal to the order of the group. So the order of the group is equal to the order of an element, and the group is cyclic. That is the plan of the proof. So we proved this. On the other hand, by proposition 1, we have that for all H in H, the order of H must divide the largest order, which is M. And so, by definition of the order of H, if we take H to the power M, this gives the identity. Now, if we apply the additive inverse of the multiplicative identity 1, so we get minus 1 over here and minus 1 over there, we must get that on the right-hand side. This is equal to the additive identity of the field 0. So we get H to the M minus 1 is equal to 0. So this means that H is a root of the polynomial pt, which is given by t to the m minus 1. If we just put h there, it is equal to 0. It is a root where the coefficients are in the field f. Since the degree of this polynomial is equal to m, then by proposition 2, we have that here, pt has at most m roots, and each of these roots is an element in H. So this means that the order of H has to be at most m. So we've just succeeded in saying that that m is less than or equal to h and m is greater than or equal to h. This means that m is equal to the order of h, which means that h is a cyclic group, completing the proof of the main result. And now, using this result, we have the following corollary. In the field of complex numbers, the nth roots of unity always form a cyclic subgroup. And for the proof, we simply apply proposition 3 with f, the field, is equal to the field of complex number, and the subgroup of the multiplicative group C star to be the nth roots of unity. So e to the power 2 pi I over n times k for all integers k. This is a subgroup of the multiplicative group C star. And that's it. That is the proof of this corollary. An example would be if we take the fifth roots of unity. In other words, the complex numbers, such that if you take the fifth power of that complex number, you get back 1. And here they are represented graphically on the real and imaginary plane. 1, zeta, zeta squared, zeta cubed, zeta to the 4, back to 1 again. All of this subgroup is generated by a single element which is zeta. So in this case, this subgroup is equal to the subgroup generated by the single element, which is the fifth root of unity, zeta. And this applies for any n. And if you look back in the drawing in the introduction, this is the case for different n's. You can clearly see the satisfying symmetry that results here for the different n's. This is for n is equal to 1. We have simply the trivial group. N is equal to 2. We have the identity and minus 1. And this is all generated by the second root of unity, which is minus 1, because minus 1 squared is equal to 1. And for n is equal to 4, we have this is 1 minus 1, I minus I, all generated by the fourth root of unity, which is I, where I generates all of these points on the circle. This has been the lesson. If you've enjoyed, please drop a like, subscribe, and share with anyone who would be interested in this lesson. I'll be dropping more content on group theory, and I'll see you on the next time. Bye.